So what I want us to do now is return to our discussion of area. And remember, we were using rectangles to approximate area. So I'll say we discussed approximating area using rectangles and right endpoints or left endpoints. So now we're going to use two new terms that we haven't seen before. So the first one is called an upper sum. So this refers to either the left or right endpoints, but it's the one that's going to estimate your area. And then the lower sum will again correspond to one, either the right or the left, but it's the one that will underestimate your area. So it depends on your shape of your graph which one it is, but just remember when you say upper sum, you want to overestimate, and when you say lower sum, you want to underestimate. All right, so now let's look at an example. So I want us to find the upper and lower sums for the region bounded by the graph of f of x, which is going to be x squared, and the x-axis between x equals 0 and x equals 2 using n rectangles. So here we're using an arbitrary number of rectangles. N represents the number of rectangles we're looking at. So the first thing we want to do is we want to calculate the width of each rectangle. If you remember, that's what we call delta x. And the way we get that is we take the length of our interval, b minus a, and divide by our number of rectangles, which is n here. So here, if I look back at my problem, I'm looking between x equals 0 and x equals 2. So b would be 2 and a would be 0. So the width of each rectangle is 2 over n. So let's draw our graph. We're looking at the function x squared between 0 and 2. So then here's 2. And I'm going to draw this. Okay, and then I have, this is my parabola, so it looks like that. And this is the region I'm trying to find the area of. I'll fill it in here for you. That's the region I'm trying to find the area of. Now, we're going to use rectangles. And let's say we want to find the lower sum first. So let me erase that shaded in region so that we can draw in our rectangles now. So remember, if we're talking about the lower sum, we want to underestimate. So think for a minute. If I choose, let's say here's my first rectangle. This distance here is delta x. which one is going to give me an underestimate? Is it going to be my left endpoints or my right endpoints? Well, it's going to be your left endpoints, because see, this first one would have height 0. But then if I go out another distance of delta x, if I pick the left endpoint, my rectangle will be inside of my region. And so if I'm looking for an underestimate, i.e. a lower sum, I should look for the left endpoints. So I'm going to call these left endpoints m sub I for the ith one, and let's see if we can figure out a pattern. So the first one, m1, for my first rectangle, I'm going to pick the left endpoint, which would be 0. And for the second rectangle, I'm going to choose the left endpoint, which means I started off at 0, but then I added this distance of delta x here, 0 plus delta x, i.e. delta x, remember though, is 2 over n. And if I looked for the third endpoint, m3, it would be 0 plus, I would go out another distance of delta x, so I would have went out 2 times delta x, so this is 2 times 2 over n. And you should kind of see a pattern starting to emerge, so I'll put dot, dot, dot here. What would mi be? Well, you've got to notice this pattern. When it's 3 here, this coefficient is 2. When it's 2, there's secretly a coefficient of 1 right there. 1 times that. When it was 1, the coefficient was 0. So it's always 1 less, so it's going to be 0 plus I minus 1 over 2 over n. Now I put 0 here because that's the start of my interval. If my interval started at a different number, that wouldn't be 0. But in general, mi will be I minus 1, 2 over n. So now let's add up the area of these rectangles. So again, we're finding the lower sum. So I'll go with little s sub n here for lower sum. And we're going to use our summation notation. So it's the sum I equals 1 to n. And then the height of each rectangle comes from plugging in our left endpoint, mi, into our function. And the width is delta x. So again, I'll label these. This is the height. And then this is the width of each rectangle. And then I'm adding up. I starts at 1, that's my first rectangle, and then n is going to be my last rectangle. Okay, so now let's plug in our definition for mi. This is going to be f. mi, the formula was it's 2 times I minus 1 over n. And delta x, remember, was 2 over n. And then what was our function? It was x squared. So now this is I equals 1 to n. So I got to square 2i minus 1 over n. And okay, well now we're going to simplify this. So if I look here, I have a 2 that's squared and another 2 that's going to be 2 cubed. The same thing for n, it'll be n cubed in the denominator, and you have an I minus 1 squared. Now all of this in the front, this is a constant. There's no variable I there. And so I can pull that out in front. And then I'm going to FOIL this part out as I minus 1 squared. If you FOIL that out, you'll get I squared minus 2I plus 1. So I'm getting 8 over n cubed. And now we're going to split up the sum that's here into its separate pieces, just like we did on a previous example. So I squared minus, and I can pull the 2 out, summation from I equals 1 to n of I, plus the summation from I equals 1 to n of 1. And now we're going to use our formulas for these three things. So the formula for the first sum, I squared, it's n plus 1, 2n plus 1 over 6, minus 2. Now our formula for I is n plus 1 over 2. And then our formula for 1 here, it's 1 times n, or just n. And now we're going to simplify this. So these 2's cancel. Let's see, this will be 8 over n cubed. If I multiply this whole numerator out, you're going to get 2n cubed plus 3n squared plus n over 6. This is minus n squared plus n plus n. Well, these two are going to cancel, this n, and that's really a minus n. So you're going to get a common denominator of 6 here. Two n cubed plus 3n squared plus n over 6 minus 6n squared over 6. And then you can combine them. This will be 2n cubed minus 3n squared plus n over 6. And you can pull this 6 out, so it'll become a 4 over 3n cubed. If I simplify my coefficients, and I can write that now, if I distribute everything back out, as an 8/3 minus 4 over n plus 4 over 3n squared. And there is my lower sum. Now, one thing I do want to mention is what happens when we take the limit of this lower sum. So if I'm looking at the limit as n goes to infinity of Sn, as I take more and more rectangles, remember it gives me a better and better approximate for my area. And here, if I take this limit, I'm going to get 8 over 3. And then these other two are going to be 0. Just comparing the degree of the top and the bottom. So the area here will be 8 over, or the limit as I take more and more rectangles, my approximate for my area will be 8/3.